So, here I am going to talk about the various topologies of this hybrid energy storage system, its power management and control classification, the architecture which we are going to implement for this DC microgrid, its simulation and the experimental validation will be explained by that is the laboratory setup in real time will be explained by my PhD student Rasmiranjan Swai after I cover all this part. So, coming to the various topologies that is available for this hybrid energy storage system, which I skipped during explaining the power management. So, here if you will see, it is a passive topology, semi-active topology and active topology, and but while explaining about the power management, I told we are taking the active topology, but in literature you will find different topologies and its pros and cons. So, if you see the passive topology, which is shown in this figure A and B, here the battery and supercapacitor, this hybrid storage unit is directly connected to the DC bus is one topology, and another is both battery and supercapacitor are connected parallelly and it is interfaced through another DC-DC converter and connected to the DC bus, which is supplying to the load. So, in this passive connection, okay, this connection means this topology is very simple, less costly because we are not having any control over here, but the main problem with this is the battery supercapacitor current as well as the DC bus voltage we cannot regulate. We cannot maintain this DC bus voltage constant, as well as we cannot have a charge discharge means controlled charge discharging of this hybrid energy storage system. Then coming to the second topology of this passive connection, here this hybrid energy storage system, this battery and supercapacitor should be means as both the cases we are connecting it parallelly. So, they should have same voltage level, and once they are connected in parallel, they are connected to the through the DC bus via this DC-DC bidirectional converter. So, one advantage is here we can regulate the DC bus voltage, whereas as they are connected here, the regulation of individual units battery and supercapacitor we cannot control it properly, means that is the disadvantage of this topology. Then coming to this semi-active topology, here I have shown you can see here this battery and supercapacitor, one either of the storage is connected through the DC-DC converter, either battery is connected to the bus through a DC-DC converter, supercapacitor is interfaced directly, and it is the reverse way, battery is connected directly and supercapacitor is through this DC-DC converter. So, again what is the drawback of this system? It is little complex than the previous one, little more costly, but the problem is the one which is connected directly it is not regulated. We are regulating the DC bus voltage, we are regulating the battery current if it is connected through the DC bus, and it is the other way around. Here if battery is connected directly, battery charge discharge control cannot be regulated. So, these are the problem with this passive and semi-active topology. So, we are going for the active topology. Okay. If we are there are several topologies available in literature, but if you have seen the architecture of PV HESS based system, wind HESS based system, we are going for this active connection, okay, where both battery and supercapacitor are connected to the DC bus through this bidirectional DC-DC converter. Okay. So, here it is, so that means we have a better control here, both charging discharging current of the battery as well as supercapacitor can be controlled in a better way. So, and the DC bus can be regulated in a very efficient manner. Okay. So, overall efficiency of the hybrid energy storage system increases. Apart from this, so we are in this our implementation, which will be explained by Rasmi after 2-3 minutes. So, this will be means he will show this connection in detail. He will explain you the corresponding sensors, how it will be developed, how it is already been developed and already it has been implemented in real time. Before that, just I want to show other topologies, which is here instead of this battery supercapacitor, one is connected through the DC-DC converter. If you will see this G and F and G, okay, and then overally after controlling the DC bus, again it is connected to the load through another DC-DC converter. So, DC bus voltage regulation as well as one of the storage unit is controlled properly. Okay. And another is the one which is having a multi input single output system. Here this is the battery and supercapacitor are connected because two inputs are connected through this DC-DC converter, this MISO system you can say, and here the this is the advanced one which we have not worked with. So, this is what the it is means the main thing is compared to the this active topology having two bidirectional converters, this is a single converter, but its implementation is complex. So, that is the main part of it. So, now coming to this is about the topology. Then, so if you will compare this is you can see here the already what I have explained cost wise the flexibility and DC bus voltage fluctuation, this has been compared here in this table. So, you can go through this slide. Now, coming to the power management of this hybrid energy storage system. So, this is the power management system which has been means already available in the literature. Okay. So, this is we can divide it into the classical control scheme or intelligent based control scheme. Okay. This is so in the classical we have several methods, but already I explained in detail about the filtration based method. Apart from this group control based, sliding mode control, the deadbeat control, rule based control, all these are coming under classical, and already I told this intelligent based control, this ANN fuzzy logic based control, though it is giving more efficient, but because of the computational burden it is giving some implementation complexity. Okay. So, we have not done in this part. So, I am not going to explain anything. So, here basically I am going to explain about this filtration based control and some modified scheme of the filtration, the conventional filtration based which I have explained in yesterday's class in detail. Okay. Then comes the this how the reference current or power of the battery or and supercapacitor based HESS system is developed or means segregated. So, here also several controls, this PI control based, robust control, gain scheduling, and this nonlinear control and fuzzy logic based control, we are going for this PI control. Okay, already you have seen. So, now coming to the architecture of this bidirectional converter which is called the active topology. So, this battery as well as supercapacitor are interfaced to the DC bus through two bidirectional converters. So, this converter design also you already know. Okay. So, this is implemented. First we have designed it, simulated it. So, I will show the simulation result. Okay. Then rest we will explain you. So, this filtration based control yesterday I have explained in detail. We are segregating the high pass component and low pass component through a low pass filter. Okay. If you will see, the net current is subtracted from the battery reference current and we are generating the supercapacitor reference current. So, this is a conventional filtration based control. Okay. First yesterday result I have shown with this type of control for this PV HESS based microgrid. Okay. Now, this control scheme is modified. Okay. And we have tried to propose another means whatever is available in literature, first we have tried that one, then we have proposed our filtration by modifying these two or merging these two, we have tried to see the overall performance of this HESS based system, and we have found that there is a performance improvement. So, that I will show with the experimental results. And this also this control scheme which first one with respect to the this conventional control. So, one is this modified filtration based thing, this is the battery reference error reference is added here to improve the overall functionality, means to reduce the DC bus voltage overshoot and the tracking time, all these things are improved. Okay. So, this DC bus voltage error based filtration based method. Okay. And this is another, instead of this I net minus IB ref, okay, here direct the measured battery reference current is subtracted and the supercapacitor reference is generated. So, that is with a slight variation, but it is improving the control scheme, the output of the overall control scheme is improving a lot. So, now merging these two with a VDC error compensation and also the battery current error compensation, we have proposed this modified filtration based control, that is our proposed method. So, we have tried to simulate this one. So, all these 4 topologies, the control schemes along with the conventional one 5, we have tried to simulate and compared. Okay. So, this is our proposed one, the overall result. So, here this is, there is no source, means renewable energy source, we have only battery and supercapacitor, where battery is supplying the main tangent part is supplied by the supercapacitor, and the steady state part is supplying, battery is supplying the steady state part. So, here you will see just the transient part, everything already this type of result, the battery current, if this is the load, and only result the condition is with the increase in load and decrease in load, we have tested or simulated this system. Okay. So, this is the corresponding VDC regulation, SOC of battery and SC are shown here, and corresponding currents. Okay. So, all the reference current, the actual currents are tracking its reference value, fine. So, this is for the proposed method, and then only this VDC, for this VDC the DC bus voltage, here we have tried to compare for all these topologies. Okay. So, how this gradual, this is the conventional one, okay, and then all those 4 control methods. How the, means if you will see the undershoot and overshoot, it is gradually decreasing. If you will see, this is the overshoot case and this is the undershoot case. Okay. For during the load change, transient operation, how the performance is improving, that is compared here. Okay. If you will see the settling time for the load increase, load decrease, and overall undershoot and overshoot for the proposed one is so less if you will compare with the conventional one. And then this paper is also we have published in already Journal of Power Sources, you can refer this is given in this reference also. Okay. So, that you can, because of time shortage I am going little fast. So, that because actual implementation he will show you, Rasmi will show you. So, this is about the simulation result. Then I think experimental validation now you can take up, it is over to you.
Now, I am going to explain the experimental validation of the overall HESS system. Here we are taking for experiment, we are taking battery pack of 12 volt lead acid of 42 ampere hour of each, resulting 24 volt and 42 ampere hour, and here the inductor is taken as 0.05 and other parameters you can see, and the switching frequency here is taken as 10 kilohertz, and the load around 4.6 ohm and 2.3 ohm. And this is the overall system architecture or the connection diagram of the system, you can see here. And here we are for the measurement purpose, we are taking current sensor and voltage sensor. The current sensor, the product serial number of the product name of the current sensor is LEM LA55P, which has a maximum current measurement up to 50 ampere, and here we are measuring only maximum current of 10 ampere, and the 10 ampere is converted into plus or minus 5 volt, and as it is a current sensor, we need a turns to turn ratio. So, for the turn ratio calculation, we are taking we are using this formula, number of turn is less than equal to the maximum rating of the sensor divided by how much current we need to measure. Here in this case, we are using maximum rating is 50 ampere and we are taking 10 ampere. To calculating this output current of the sensor, it will be become 0.05 ampere. And this sensor has also 1:1000 conversion ratio. For the number of 5 number of turn, we have Imax of 10 ampere. So, output current will be become 0.05 ampere. So, input current of 10 ampere, the output measuring resistance which we are seeing here ROI, that is connected to the ground and the output voltage, the output point. So, here the resistance, output resistance will be around 100 ohm. So, some important point to taken care of while using this sensor. The output resistance should not be selected beyond 150 ohm to avoid non-linearity in the measurement reading, and to increase the accuracy in the measurement, reduce the effect of temperature changing, the maximum power dissipation should be around half watt or 1 watt. So we are using LEM LV25P Hall effect voltage sensor for the voltage measurement purpose. Here is also the maximum voltage can be measured here at the range of 10 to 500 volt, and it operated at plus or minus 5 volt 15 volt supply power supply. The manufacturer data sheet provided that the primary current of this sensor is 10 milliampere, and this sensor has 2500 is to 1000 conversion ratio. So here is also we are selecting the output sensor and the output resistance and input resistance connected to the system. So here are the relation, so that we calculate and the maximum power dissipated at this sensor module is around 2 watt. So here is also some points to be noted. The output resistor should not exceed should not be selected beyond 300 ohm to avoid the non-linearity, and to increase the accuracy. So here is also we consider the maximum power dissipated here as 1 watt or half watt or 1 watt maximum. So now coming to the controller part. Controller for this implementation, we are using DSpace DS1103 digital controller board, which has you can see the which has some two processor such as master PPC and slave DSP 4240 F240 processor. These two separate controller. So it will use it to generate the control signal for the switches. To control this software, to control this board, we have a software named Control Dex, which is integrated with MATLAB and RTI library, where you can see later in the next slide. This is the overview of the image of the controller. You can all the channels and the output input port are displayed or marked on the screen. The first and the number marked with 1 is ADC channels, which is from and the number marked in the second box maintains the DAC channel. Next two connectors are slab ADC channel and digital IO input output channel. The fifth one is the slab input IO output channel, and seventh is the CAN connector, and so on. This is the digital the master PPC. This is the layout of the master PPC or the master controller. Here we have some. This is generated from the MATLAB library. We can see by typing RTI, and it will display the available ports and connectors with this board. And in the right side figure, that depicts the connect or the pin available with the master PPC controller. Here you can see the serial numbers of the pins and the port associated with this system. The input output resources of this board are split between two processors on the board, the master PPC as I said, and the slab DSP F240. By clicking on either of, you will have access to blocks that can be placed on your model that provided input output functionality associated with the respective processor. I was talking about this this library. Now similarly, for the slab DSP, this is the connector of pins, and this is the blocks available for the MATLAB integration. And before going to MATLAB, the simulation or hardware implementation, these are the steps we have to follow to configure our hardware environment or the software environment. Now we are coming to MATLAB to follow these steps. If I type RTI, it will display the boards available with the system as I display. Here you can see two controller board or individual processor is available, master PPC and slab DSP for F240. If you double click on master PPC, the available blocks will be displayed here, and similarly the slab DSP also, These are the display available. These are the library available to integrate with the MATLAB. To run the environment, first we have to set up this system by clicking new simulation model. After creating new model, we have to configure the parameters as mentioned in the slides. First, we have to save the model and set the stop time to infinite. First, we have to go to the model configuration parameter. Here, we have to set the stop time to infinite. Then open and edit configuration. These are that I have already opened. Set the solver parameter to OD1 Euler. Here OD1 Euler is selected. Then go to all parameter. Fixed step size should be multiple of sample time. So whatever sample time we took, then that will be multiple of the step size. Should be checked. Suppose I am taking 0.001. And third step is uncheck the optimization. Here we have to search for the parameters. Then the hardware configuration settings is displayed here. The system target file should be, by default it was grt.tlc here, grt.tlc, but for our system we have to select our this rti1103.tlc, which is this space target file. and some other parameters we have to select. For optimization, block reduction optimization, by default it was on, then we have to keep it off. Go to all parameters, search for block reduction. Block reduction by default it is on, we have to turn it off, apply. Then signal storage reuse, we have to turn it off also. Signal storage reuse here, we have to turn it off also. Then conditional input branch execution. Conditional input branch execution, turn that off also. And the system target file, we already set this to RTI1103.tlc. And after setting this system other parameter, we have to create our model. So to save time, I have already created this model. Let's go through this model. This is the model. First we have to input the import the measurements we have taken from the system. Now I am going to show the various input sensors associated with the system. This is the controller board RTI D-space RTI1103, and the control signals are generated, and the whatever I showed, the master slave ADC or the digital IO or the slave DAC, that ports are connected and the input are given there. Also the output is taken from the those ports. And this is the battery model. Each one is having 12 volt and 42 ampere hour. So combined we are getting 24 volt and 42 ampere hour. And this is the supercapacitor we are using, which have rating of 58 farad, and each series have voltage rating of 16.2. Though combined it is getting 32.4 volt and 50 farad. This is the sensor module, the current sensor module, and this is the sensor module for supercapacitor, and this is the voltage sensor or the voltage sensor module for the VDC or load. This is the LV25 voltage sensor, and this is the LEM25 current sensor. And these are the converters associated with the system. The right side of the green light blinking in the converter, that was representing the supercapacitor module, buck boost converter for supercapacitor, and the red one is associated for the battery. Now let's coming to the modeling. The model we are taking here. Let me zoom. Here we are taking the voltage measurement from the voltage sensor through ADC channel of. If you double click on that channel, it will show the channel number. So here we are taking from channel number 19. So channel number 19 will provide the input for the voltage sensor from the voltage sensor and provide it to the controller. And here we are taking 48 voltage as voltage reference or VDC ref. We are giving the to filter out the noise, we are using this transfer function, and this is the sensor gain. For the sensor we are getting voltage gain of for the controller we are getting 10 voltage rating voltage gain of 10, or the gain of 10 from the controller board. If we provide 10 plus or minus 10 volt, the controller will scale it down to -1 or +1 volt. So we are getting around 10 of gain of 10. Similarly, the sensor also has some gain. So if we multiply, so sensor has gain of 40 and this controller has gain of 10. So if we combine those gain, we are getting 400. So the input signal is passing through the transfer function to filter the noise, and the gain is added to get the actual system voltage. So these voltage are compared here, and the error is fed to the voltage controller. Voltage controller block has a PI controller which has the proportional or integral value which are tuned separately, and the output of this voltage controller block will be the total reference current for the HESS. So now the HESS is now the output of this voltage controller is given to the HESS system. So now it contains both the combined output or the combined current reference, which will again fed to the filter. So madam has already explained the filtration based control. So the filter is presented here. It will separate the high frequency component and the low frequency component of the system. The high frequency component of the the reference current will be the reference current for the supercapacitor, and the low frequency current, the low frequency parameter of the is the reference current for battery. So that is done here, and the output is going through the filter, first order filter, and the output of this filter will be I battery reference or battery current reference. And if we if we subtract the this reference current from the total reference, then we will get the reference current for the supercapacitor. That is done. Similar thing is done here. Now we are getting the battery reference current, and here this block subtract this battery reference current from the total reference current. Now this we get two reference current for battery and another one for supercapacitor, ISC rep, and I battery rep and ISC rep. Then I battery rep is compared to the I battery actual or actual battery current, which is also imported through the here I battery actual. It is imported from the measurement by using ADC channel of channel number 18. So here is also we are using the transfer function to filter the noise, and here is the sensor gain. So after that we are getting actual battery current. The actual battery current is again compared to the reference current, and the error is fed to the another controller block, that is PI, that is also PI controller, and that output of the controller block will be the duty ratio for the battery. Similarly, with the supercapacitor also, we are getting reference current for the supercapacitor, ISC reference, and it is again compared to the actual supercapacitor current, which is imported from the using ADC channel of 14. This is a master multiplex converter. So it has 4 channel inbuilt, the merged together, and the converter number 4 will provide 4 individual channel. So from that we are taking only one channel. The first channel we are taking, so it will be channel number 13. So again it is filter, noise is filtered by this transfer function, and the gain is added. So after that we are getting actual supercapacitor reference current, that is compared with the generated reference current of supercapacitor. So both error will be fed to the supercapacitor controller, which is also a PI controller, and the error of the output of the controller block will be the duty cycle for the supercapacitor converter. That was I explained previously. So now we are getting 2 different duty cycle. So we have to forward those duty cycle, or convert the duty cycle into PWM pulse, so that our converter will run. So to give the output from the system, we are using this also. They also provide the output DAC channel. We are using this PWM here to import the signal from the measurement port, we are using master slave master ports. Here we are using DSP, 3-phase PWM generation. It is a slave port, and here we are giving the frequency as 10 kilohertz, and it has a 3-phase PWM three-phase PWM port. For the 2 ports, we are giving duty cycle for one for battery and another for supercapacitor, and the third port will remain open. So these are the rest 2 blocks are using for. Here we get the I battery current, and these 2 blocks are used to retrieve the SOC of the battery and for supercapacitor. After now the model is generated. So after modeling, the model has generated, we have to build it. So this is the build option. So after I click this build option, the MATLAB will generate the MATLAB has started the building process. The code will be automatically generated. So you have to wait till then. Now the build process has completed successfully. So the build process has generated some file with SDF name, SDF extension. So the SDF file will contain all the necessary code parameter or the blocks that will we use with the controller board. And the controller and this SDF file will be stored in the MATLAB home directory or the folder, home folder, root folder. Here you can see the untitled.sdf folder. So in control desk, to control to use the associated after building a model, you have to control the board using the software provided with it, which is DSpace control dex 5.6 of 5.6 version. In this control desk, first we have to create new project plus experiment and giving it a name. I am giving the project as and we have to also choose the root directory. And after the choosing giving the name and root directory, it is asking for the experiment name. Suppose I am leaving it by default, and here we have to choose the platform. Platform is already chosen 1103. And after choosing this, we have to choose the SDF file. SDF file is located at the root directory of the MATLAB. So we have to browse the file from there. And after selecting this file, you have to finish. Have to click the finish. Now the new environment has created. So it is initially it was blank. So we have to import all the variables available with the model. For that we have to go to this all variable description, then model root, then we have to expand it further. Here we are getting this I load. Here first we have to import the battery voltage. Click after selecting battery voltage, in this variable bar it is option is showing. So click on this bar and try to drag it up to the blank screen above. If we leave the cursor, these are the options available at the time. So first we have to use the time plotter to display the plot the values. And also we have to see the value in the real time. So again click it, drag it and drop here. The display option will be available. So click the display. Similarly, we can do this for other parameters also. This is SC means supercapacitor voltage. Click drag in and drop it in the time plotter to plot the variable, and also to display it. Again drag and drop and open the display. Similarly, for DC ref, the DC reference or BDC reference voltage, drag it here and drag it here. Here I am taking battery voltage, supercapacitor voltage and BDC reference, BDC actual, associate of battery and supercapacitor, then total reference current. Then battery reference current, then supercapacitor reference current, then the actual currents available. So after adding this variable, we have to save the model, save project, and some other settings we have to do. First go to properties, then instruments, and to save the recording, we have to add and go to recording, then create new record and double click on that, open properties, and we have to change the format of the recording. Give it the name prefix, so if it will sequentially added or renamed automatically by recording underscore here, and also turn on automatic export. Now export file format should be in MATLAB file or .mat here. So for future use, it will be the data will be stored in .mat file, and we can use it to plot or analysis for future analysis. Then we have to save the project again and click on go online. Now we can see the reading from the sensors. Here we have a battery voltage of 23.8 volt and battery SOC around 78%, and here supercapacitor and VDC reference voltage at 48 volt. And after that, click on start measuring. That time plot will show the the real time reading from the sensors. Now we can turn on the switch of the controllers. जो बोलूँगा. Now we can see the VDC is tracking. You can focus there, around 47.3 volt. So the time plot is now recording the, or after that we will have to click the recording by clicking on start immediate. So it will start the recording. If I try to change the load, then now the controller also able to track the voltage. Here battery current, a total reference current is generated as here you can see the battery is getting discharged and time plot is recording. And after completion of the experiment, then we have to click the start stop recording option. And after that stop measuring and go offline. I click on go offline, the pulse generation will be stopped. So the file is saved here. Here you get experiment data in math format. You can import it to the variable, and you can try to plot here. The one demerit of this system is the data is stored if we are adding it sequentially, but the data is stored randomly. So we have to find it which data it was. Now the data is exported to the system, and if I try to display by using this code, now see here this data is saved, and we can plot it by using MATLAB command. See, there are two variables are stored. Or problem is you have to find the which data it was. So by identifying our system, we can easily do that. These are already explained. So we have to save the file name and exported the automatic export, and the file data type should be in math format, so that we can use it in for future analysis. Here you can see. Now this is the result I already previously taken. Here the result you can see the initially, and the orange one depicts the battery power, and the blue one is the PV load power, and the yellow one is the supercapacitor power. Here the load is initially it was around 180 watt, and the battery is able to provide it completely, and at the stage sorry, the load is at around 200 watt, and at 15 seconds the load is increased to 300 watt. Now you can see the battery power is getting providing the steady state component, and the supercapacitor is getting a spike at this 15 seconds. So this will represent the transient, and it is handled by the supercapacitor. Now, the right side plot is depicting the current current output of the system. Similarly, the orange one is the reference supercapacitor reference current, and orange and black are both representing battery current, and blue one is the load current. Here you can see the battery is trying to provide the steady state power, which is in almost constant form, and there is a spike also present in the at 15 second and 25 second. At 25 second, the load is reduced to again 200 watt, which is clearly visible in this graph. And this is the voltage, the DC bus voltage tracking using experimental method, and all other methods are filtration, all the other control methods are compared here. So we can see here the red one is the fast small axis is the actual the proposed control method. Here you can see the smoothing of the transients, and the undershoot of the system is also very low. Here also you can see other different available control strategy we have already tested. Now these are the references. Thank you.